Thermodynamics and Hess's law. Two terms that we have to define before we start. What's the difference between enthalpy of formation and enthalpy of reaction? The standard enthalpy of formation, written as delta H0F, which is a notation, can be defined as the enthalpy change when 1 mole of a substance is formed from its elements in the standard state, or we call it SATP conditions. Here is an equation: carbon in the solid state, which is graphite, plus oxygen in the gas phase will undergo ignition or react to produce carbon dioxide, and that releases about 393.4 kilojoules of energy for every mole of carbon, or delta H0F is referred to as minus 393.4 kilojoules per mole, which is called the heat of formation of carbon dioxide, or enthalpy of formation of carbon dioxide, or standard enthalpy of formation of carbon dioxide. In this reaction, the reactants are elements and 1 mole of the product is formed, hence the unit kilojoules per mole. When we talk about standard ambient temperature and pressure, the temperature is 25 degrees Celsius or 298 Kelvin when you convert degrees Celsius to Kelvin, and pressure is 100 kilopascal. That is implied every time we say the reaction takes place at SATP conditions. If the condition is STP, then the temperature changes to 0 degrees Celsius and the pressure would be 101.325 kilopascals. Standard heats of formation of all elements in the periodic table are taken as 0, so those values will not be provided for you. Enthalpy of reaction, delta H0R or Rxn. The total amount of heat energy evolved or absorbed, which means released or absorbed, when the given moles of the reactant react completely to give products as in a balanced chemical equation. The reactants, at least one of them, should be a compound for the reaction to be considered an enthalpy of reaction. The enthalpy change for the reaction can be calculated using the equation delta H0R is equals to sum of the enthalpy of the products minus sum of the enthalpy of the reactants. This is the equation that we're going to use for most of the problems. Here this sigma represents the sum of the products and sum of the reactants. Here is the equation: methane 1 mole plus 2 moles of oxygen gives you 1 mole of carbon dioxide and 2 moles of water. And delta H for the reaction is minus 890.3 kilojoules. The reaction is exothermic because delta H is negative. This equation is balanced, so it tells you every time 1 mole of methane undergoes complete combustion, it can produce minus 890.3 kilojoules. Some of the common enthalpy changes you may encounter while learning chemistry or thermodynamics: enthalpy of combustion, which was an example that we just discussed; enthalpy of neutralization, a reaction between an acid and a base, has energy changes involved. It's an exothermic reaction. Enthalpy of fusion, it's melting of a solid to a liquid. The heat change associated with the physical change is what we are referring to as enthalpy of fusion. When ice melts, the enthalpy change is referred to as enthalpy of fusion. Enthalpy of vaporization, when 1 mole of liquid water changes into gas at the boiling point, we can calculate the enthalpy of vaporization or enthalpy of sublimation. Some common enthalpy changes for physical as well as chemical changes is what this slide represents. Here we are going to determine the enthalpy change, and primarily there are 3 methods used to determine heat change or enthalpy change. One is from the bomb calorimeter. If you use a closed system like a bomb calorimeter, the enthalpy change is usually referred to as internal energy because heat change at constant volume is considered internal energy. The second one would be determining enthalpy change at constant pressure, and usually we use Hess's law for that. Or delta H is equals to sum of the enthalpy of products minus sum of the enthalpy of reactants, and we will be using heats of formation of reactants and products to determine the enthalpy change. Or if you know the enthalpy of reaction, we can determine the heats of formation of any one of the unknown compounds. The third method for determination of enthalpy change is from bond enthalpies or bond energies. Mind you, there is a small difference in the equation here from the second one. Delta H reaction from bond enthalpies is equals to sum of the enthalpies of the reactants minus sum of the enthalpy of the products. These may also be called at heat capacity at constant pressure or enthalpy change for the reaction using bond energies. So three methods to determine enthalpy changes. We have already done the first method, calorimetric calculation. We are now at the second point, which we are using Hess's law to determine the molar enthalpies or heats of formation, as the case may be. If enthalpy of the products are lesser than the reactants, the value of delta H is negative and the reaction is considered exothermic. And if delta H is positive, or if energy is given off, or if energy is absorbed, then the reaction is considered to be endothermic. Thermochemical equation. A balanced equation that includes energy and the states of reactants and products is called thermochemical equation. CH4 plus 2O2 giving you CO2 plus 2H2O plus 8O2.2 kilojoules. This is one way for writing a thermochemical equation. The reactants and products, we indicate the physical states of those reactants and products. And we also include an energy term, and in this case, heat is considered a product in the reaction. So we may write it like this. We may alternatively write it using enthalpy or delta H values. In that case, the equation looks like this. CH4 plus 2O2 gives you CO2 plus 2H2O. We have separated the energy here and we have written it as enthalpy of reaction is equals to minus 802.2 kilojoules. Here, the sign convention for energy release should be adopted. So delta H is negative. This is an exothermic reaction. And the third method is a possibility. We don't do that frequently. We write the energy term along with the reactants. So we are taking away 802.2 kilojoules. In that case, the equation would be CH4 plus 2O2 minus 802.2 kilojoules gives you CO2 plus 2H2O. All three equations represent the same reaction and they are all considered to be right. Or we can say if 1 mole of methane releases 802.2 kilojoules of energy when it undergoes complete combustion. Hess's law, the heat change evolved or absorbed in a particular reaction is the same whether the reaction takes place in one step or in several steps. We have to determine the enthalpy changes for reactions, which normally cannot be determined or cannot be performed in a lab. Then we use Hess's law to determine enthalpy change for the reaction. For instance, if I give you carbon, hydrogen and oxygen, you cannot mix it to obtain either methane or glucose or any compound for the matter in one step. But we still want to determine the enthalpy change for the reaction. In such cases, we adopt Hess's law, and it kind of works very well. So here is an example to illustrate Hess's law. I have carbon here in the solid state. When I say carbon in the solid state, it is graphite. It is going to react with oxygen to produce carbon monoxide. And the enthalpy change associated with the formation of 1 mole of carbon monoxide is minus 110 kilojoules. Now, you can take carbon monoxide and change it into carbon dioxide. We can oxidize it. If that happens, the energy change associated with that is minus 283 kilojoules. Both of these reactions are exothermic because the sign conventions tells us a negative value for enthalpy change indicates an exothermic reaction. So changing carbon to carbon monoxide releases minus 110 kilojoules, and changing carbon monoxide to carbon dioxide releases minus 283 kilojoules. So if we were to convert carbon directly to carbon dioxide, what would be the energy change involved? So If that is true, the amount of energy released would be minus 393 kilojoules, which means the reaction is taking place in one step. But if the reaction takes place in two steps, if you add up the energy changes, that will give us the enthalpy change for a single step reaction. Or H1, H2, and H3 are the enthalpy changes for each of these steps. If you add up enthalpy change for delta H2 with delta H3, that will be equal to enthalpy change for the reaction. So this is the basis of Hess's law, the algebraic addition of the enthalpy changes for the different steps in a reaction. We can also convert the reactants to the products in a single step. We can actually obtain the value merely by adding the enthalpy changes for each of the steps involved. We can use this to determine the enthalpy change for any one of the steps that is unknown. So the equation that we are going to use to determine the enthalpy of reaction is delta H reaction is equals to sum of the enthalpy of the products minus sum of the enthalpy of the reactants. This is the equation we're going to use. So here is a problem for you. Calculate the enthalpy of combustion of methane. The standard enthalpies of formation of methane are given, carbon dioxide is given, and water is given. The values are, the standard enthalpy of formation of methane is minus 74.85 kilojoules per mole. The value of standard enthalpy of formation of carbon dioxide is minus 393.5 kilojoules per mole. And the standard enthalpy of formation of liquid water is minus 286 kilojoules per mole. Those values are given to you. You're also provided with the heats of formation data sheet. You may use these values or obtain the values from that data sheet. Now we are supposed to calculate the enthalpy of combustion of methane. So in order to do that, we will use a very simple method based on the equation that was given to you in the previous slide. Delta H reaction is equals to sum of the enthalpy of the products minus reactants. This implies we need an equation that is balanced, which can be used to calculate the enthalpy of reaction. So we will write a balanced chemical equation. CH4 gas plus 2O2 gas gives you CO2 plus 2H2O. And we need to find out delta H, which is the unknown. Okay, then we will rearrange this equation in the form of the equation needed for solving to determine the delta H0 reaction. Here is the equation we're going to use. Now I'm changing the products into the actual products that are being used. In this equation, you'll find on the right side of the arrow, which we get the products, we have carbon dioxide and 2 moles of water in the balanced equation. So sum of the enthalpy of the products. So delta H0 reaction is equal to sum of the enthalpy of water plus sum of the enthalpy of carbon dioxide, which would be the reactants, minus sum of the enthalpy of the reactants, which is methane and oxygen. Now in the balanced equation, we know with the products, there are 2 moles of water and 1 mole of carbon dioxide. So we are going to replace the value of the enthalpy of formation of water and carbon dioxide in the previous equation. So we can write it as delta H0 reaction is equals to sum of the enthalpy of water. So enthalpy of formation of water, there are 2 moles of water, therefore 2 times minus 286 kilojoules plus 1 time minus 393.5 kilojoules for the formation of 1 mole of carbon dioxide. That's the value for the reactants. And the products are methane and oxygen. The enthalpy of formation of methane is minus 74.8, and we have 1 mole of methane in the balanced equation, which is a reactant, plus we have 2 moles of oxygen. We have already stated that the enthalpy of formation of oxygen or any elements for the matter is 0. So 2 times 0 gives us 0. Let's multiply the values that are in the brackets. When we multiply 2 into 286, we get the standard enthalpy of formation of 2 moles of water is minus 572 kilojoules. Carbon dioxide is minus 393. And for methane, it is 1 times minus 74. And for oxygen, it's 0. So we're going to apply this equation, delta H0 reaction. We will add up the enthalpy changes for water and carbon dioxide on the product side. That value becomes 965 minus 572 plus minus 393 gives us minus 965.5 kilojoules would be the enthalpy change of the products. And enthalpy change for the reactants would be minus 74.8 kilojoules because oxygen is 0. Further simplifying, delta H0 reaction is equals to minus 890.7 kilojoules per mole of methane. Value is negative, it's an exothermic reaction, and you know that methane, when it undergoes combustion, produces heat energy. It's an exothermic reaction. Or we can say the enthalpy of combustion of methane is minus 890.7 kilojoules. So delta H reaction is equal to sum of the enthalpy of the products minus sum of the enthalpy of the reactants. That's the final statement, and we will go to the next problem. Calculate the standard enthalpy of formation of methane if the heat of combustion of methane is minus 890.65 kilojoules per mole, and the standard enthalpies of formation of water and carbon dioxide are minus 286 kilojoules per mole and minus 393.5 kilojoules per mole. So here we are calculating something different from the previous problem. Here you are supposed to calculate the enthalpy of formation of methane. You know that you cannot prepare methane in the lab by taking carbon and hydrogen and combining them directly. It's impossible. So that's the real application of Hess's law. But you can allow methane to undergo combustion, and you know that it will produce 890.65 kilojoules. And we already have the values for the standard enthalpies of formation of water and carbon dioxide. We are going to use all of this and Hess's law to determine the heat of formation of methane or molar enthalpy of formation of methane. Delta H reaction is equals to sum of the enthalpy of the products minus sum of the enthalpy of the reactants. So we are going to consider the reaction. The reaction is combustion of methane to give you carbon dioxide and water, and the enthalpy change is given in this case is minus 890.65 kilojoules. So we're going to write the equation as in the second line. Delta H0 reaction is equals to sum of the enthalpy of the products, which is water and carbon dioxide. So we have 2 moles of water, so 2 into H2O plus 1 mole of carbon dioxide, minus the reactants. The reactants delta H0F for methane is not known, that's the unknown quantity. And delta H0 oxygen is always 0 because it's an element. So substituting the values, delta H0 reaction is equal to sum of the enthalpy of water. There are 2 moles of water in the equation, therefore 2 times minus 286 kilojoules plus 1 time minus 393.5 because we have 1 mole of carbon dioxide. Those two are the products, minus the reactants. H0F, CH4, we do not have that value. We are going to solve for it. Oxygen is taken as 0, 2 into 0. So delta H0, which is minus 890.65 kilojoules, is equals to, when you multiply 286 by 2, you get minus 572. And for carbon dioxide, it's just minus 393. So what we're going to do here at this point is, we're going to rearrange the equation so that we have the unknown on the left side. The unknown here is H0FCH4. So what I'm going to do is, I'm going to bring the unknown to the left. When you bring minus H0FCH4 to the left, it becomes positive. And then I will take delta H minus 890.65 to the right. That will turn positive. So H0FCH4, which is the heat of formation of methane or molar enthalpy of formation of methane, is equals to H0F for water plus H0F for carbon dioxide minus enthalpy of reaction. So delta H0F is equals to minus 965 minus of minus 890.65. So that's going to give us delta H0F is equals to minus 74.85 kilojoules, which is the molar enthalpy of formation of methane or heat of formation of methane. So we have seen two different problems. In the first case, we found the enthalpy change for the given reaction. In the second case, we had the enthalpy change for the reaction. We determined the enthalpy of formation of one of the unknown substances here. So we can say the enthalpy of formation of methane is minus 74.85 kilojoules per mole.